So this is part 2 of 8.4. I just follow the same numbering as the textbook. 8.4 deals with solving equations, and we've looked at solving exponential equations. Now we're going to look at solving what are called logarithmic equations, which shouldn't come as a surprise to you. They're going to be equations that involve logarithms. We have to check for extraneous roots, and I want to just at the outset here explain why. First of all, an extraneous root is an answer to a question that you get when you algebraically solve an equation properly, but you end up with an answer that just doesn't work. You encountered this last year when you solve radical equations, equations that have square roots. And the first step, or a step in solving a radical equation, is at some point to square both sides to get rid of the radical. And then you end up solving an equation that's not technically a radical equation. And you might get an answer that when you put it into the original equation results in you attempting to take the square root of a negative, which is not allowed. So there's a restriction there. And the restriction in terms of today's content is that if you have a logarithm, and it doesn't matter what base it is, of some argument, that argument must be greater than 0. You cannot take the logarithm of 0, and you cannot take the logarithm of a negative. We've talked about this before, but briefly, just to cover our tracks again, if I say what is the base 2 logarithm of 0, then I am asking you to find a number to which 2 is raised to give 0. Well, 2 raised to any number that's in our universe of math, 2 raised to any number will never give you 0. It'll always give you a value greater than 0, which is why the function 2 to the x has an asymptote on the x-axis, and y is always greater than 0. So this doesn't exist. If I say, well, what is the base 2 logarithm of negative 8? That doesn't exist as well. I mean, this here is saying 2 raised to some exponent is 0, and that's an impossibility. This is saying 2 raised to some exponent is negative 8. And although you can't compare impossibilities, I think the second statement is even more impossible. To me, it just makes even less sense. So the argument of a logarithm must be greater than 0. All right, let's take a look at these. Starting off with 1a, it's a very, very simple question, and same with 1b. It's very similar to solving an equation dealing with exponential functions, where you have 6 to the x plus 1 equals 6 to the 8. If I said solve 6 to the x plus 1 equals 6 to the 8, you would say, I hope, well, if these are equal and the bases are equal, then the exponents are equal. And you would subtract 1 from both sides and get an answer. It's the same logical step here, that if we have a base 6 logarithm of a thing being equal to the base 6 logarithm of what appears to be a different thing, those two things have to, in fact, be the same thing. So we're not dividing by logarithms or anything. We're just using logic here and saying 2x minus 1 is equal to 11. And then you can subtract 1 from, or add 1 from to both sides and get 2x equals 12, which means x is equal to 6. But what we have to do is make sure it's correct. We have to make sure that if I put 6 in for x, I will not be taking the logarithm of 0 or a negative. So when I put 6 up here, this becomes log base 6 of 2 times 6 minus 1, and we can stop there. It's such a simple question that you can see we get the right answer. But we can stop there because you say 2 times 6 minus 1 is a positive number, which means our value for x is a legitimate solution. Okay. So very similar kind of idea to the equation on the left, except that this is not a single log equals a single log. We can put these together, though, and write this as log base 7 of 4x equals log base 7 of 12. And this very basic example is illustrating to you that if you can work towards having one logarithm equal to one logarithm, then you can drop the logarithms. It's kind of like finding a common base. This means that 4x must be equal to 12. Dividing both sides by 4, you get x is equal to 3. And since 3 is a positive number, and x is 3, and x is the argument, we're okay. We don't need to worry about kicking any solutions out because they're not valid. Any questions with the basic idea here between A and B? Well, what if it's not a log? Instead, it's a log equals a log. What if you have a log equals a number? Well, there's a couple of things you can do here, but I would recommend writing it in exponential form. So if I write 2 raised to the 4 equals x plus 3 squared, then I have an equation I can solve. So in A and B, what you are working towards is a base b logarithm of something equals a base b logarithm of an apparently different thing, so that you can set these two arguments equal to each other, because even though they may appear different, they must be the same. What we are talking about here in this question, and D as well, is going to be this idea, that you want to try to get log base b of some argument equals a non-logarithm. Because not every term is a logarithm, so we can do this. And that means you can write b to the c equals a. Which we've done here. We've written the base raised to what the logarithm is equal to, 4, equals x plus 3 squared. So we can simplify this x plus 3 quantity squared means x plus 3 times x plus 3, which gives me x squared plus 3x plus 3x plus 9, which means I'm left with this quadratic equation to solve. Are we okay with that? Yeah. Pretty basic quadratic equation to solve. We can use factoring. X plus 7, x minus 1 equals 0 is the correct factored form, which means that x is equal to negative 7, x is equal to positive 1. There are two solutions. Are they both allowable solutions? And that, I've always kind of hated saying that, because if it's a non-allowable solution, it's not a solution, right? But what I'm saying is, are these in the domain of x for this equation? And the answer is yes, because the argument is something squared. The original equation is the base 2 logarithm of that. So it doesn't matter what x is, when you add 3 to it and square it, you're going to get a positive. There is one exception. There is a value of x that is not permissible for that logarithm, and the answer is negative 3. Negative 3 is not permissible, because you would get the log of 0. But any other number, even the negative 7, when we put negative 7 up here, this is going to become negative 7 plus 3, which is negative 4, but it's squared. Okay? And that would make it positive. Over here, we want to work towards this. There's another way to do it, but I haven't even decided if I'm going to show it to you. I can do that by subtracting one of these logarithms to the other side and having the base 10 logarithm of 8x plus 4 minus the base 10 logarithm of x plus 1 equals 1. And then, using my laws of logarithms, I can say the difference between two logarithms is the logarithm of the quotient of the two arguments. And this is equal to 1. Now I can write it in an exponential form. This is a base 10 logarithm, which means I can write 10 to the 1 equals 8x plus 4 over x plus 1. And I'm getting to a point where it's not a junior high question, but it's about to become one. Because whenever you have an equation that has a fraction, and this whole right side is a fraction, it's better if we don't have a fraction. Call it cross multiplication if you will, but the general idea is I'm going to multiply both sides of this equation by x plus 1. So I need to multiply the 10 by x plus 1 and the 8x plus 4 over x plus 1 by the x plus 1. I just rewrote it because I didn't want to cram in the x plus 1's up here. You know, you would probably have room to just write x plus 1, x plus 1. So what happens, of course, is this cancels, mission accomplished, and now you're left with a junior high-ish question. 10x, boy, I'm just running the gamut of all of the different colors here. 10x plus 10 equals 8x plus 4. Subtract 8x from both sides and get 2x. Subtract 10 from both sides and get negative 6, which means x is equal to negative 3. Now, do you want to be careful? Are we okay with the algebra there? Any questions? Okay. You want to be careful in jumping to judgment here. Just because we got a negative value of x doesn't mean you're going to throw it out because you can't take the log of a negative. You need to look at the original equation. If x is negative 3, will 8x plus 4 be positive or negative? It will be negative. So that's why we're going to throw it out. And it doesn't matter whether one of the arguments is no good or they're both no good. If any argument is negative or 0, the answer that leads to that is gone. So since negative 3 leads to a negative argument, this is extraneous. And on a written response, I think you should state that. There's something else I want to talk about, though. And this is tricky, but you need to know this. If we take a look at the arguments here, the arguments are 8x plus 4 and x plus 1, correct? These must both be greater than 0. And sometimes, and I will do this on my exam, I will say solve this logarithmic equation and state the domain of x for it. If I solve this inequality on the right, I get x is greater than negative 1, correct? If I solve this inequality, I get 8x is greater than negative 4, which means x is greater than negative 1/2. Are you with me? One of these domains is already covered by the other domain. Okay? And it may not be obvious, so I really believe a number line is helpful here. Here's negative 1/2, here's negative 1. Whoop. Here's negative 1, here's negative 1/2. Right? We need a domain that covers both of them. And this will be very important, I believe, for the next unit. These two numbers are not allowed because they would make an argument 0. What one domain says is this, and what the other domain says is this. Are you with me? The domain that covers both is the overlap of the domains. It's a visual thing, and the place where they overlap is here. So the domain of x for this equation is x is greater than negative 1/2. And you can think of it logically this way. If it's greater than negative 1/2, it's already bigger than negative 1, so we don't have to worry about the negative 1. So rather than taking this number and putting it back in and seeing if we get negative arguments, you look at that number and you look at your domain, which we've just figured out, and you say that negative 3 is not in the domain of allowable values of x, and that's why it's extraneous. It's a more sophisticated response, but it's the one we're looking for in a written response, rather than just saying, when I put it in, I get a negative. All right. Well, what about this one? We're going to go log base 2 of x minus 6 plus log base 2 of x minus 4 is equal to 3. So we will be able to pack those two logarithms together, just checking my work here, and then have a single logarithm equals a number, and then write it in exponential form. By the way, do you agree that these are the two domain restrictions for each of the two arguments? That if you wrote x minus 4 is greater than 0, you would solve that and get x is greater than 4. Which of these two restrictions includes the other? In other words, if we just had to write a single statement, what would we write? Would we write x is greater than 4, or would we write x is greater than 6? 6, good. So this is the test for our answers being valid or not. Whatever we get for x, it's got to be a number greater than 6. Writing this in exponential form gives 2 to the 3 equals x minus 6 times x minus 4. So we get 8 equals x squared minus 10x plus 24, I think is correct. Subtract 8 from both sides because that's what we do when we solve any quadratic equation. We want to zero it. I don't know why I'm questioning myself there, but 24 minus 8 is 16, isn't it? Okay. This is factorable because there are two numbers that multiply to give 16 and add to give negative 10, and they are negative 8 and negative 2. Which means x equals 2 and 8. And you know, if it were a written response, you'd probably write x minus 2 equals 0, x equals 2, x minus 8 equals 0, x equals 8. But our restriction is x has to be greater than 6, which means that is not a solution. And you know, I can't write down everything in my lesson, but I can tell you that if you're doing a written response, you should write a sentence there explaining why. You've already demonstrated the domain for x is x must be greater than 6. 2 is not in the domain, so 2 is not an actual solution. I wouldn't even use the word actual. So 2 is not a solution, period, despite what the math tells us. All right, so don't write anything down just yet for this question. If we do with this what we did here, which is to have a single logarithm equal a number and write it in exponential form, then it becomes this. Do you agree? How would we solve this? Well, this is a polynomial equation. You would have to take x squared minus 8x times itself 5 times. And then you'd have to figure out what 3 to the 10 is. And then you would subtract 59,049 to the other side, where you would get a polynomial equation equal to 0, and it would be a degree 10 polynomial equation, which for you to solve would involve you factoring it, which would mean you would look at potential zeros being factors of 59,049, find one, do synthetic division to get a degree 9 polynomial function, and repeat and repeat and repeat and repeat until you got down to a degree 2. And there's no guarantee that it's factorable into 10 factors. Okay? So, no, we don't want to do that. Okay? What we want to do instead is bring that 5 down and then divide by 5 to work with smaller numbers. So if I bring that 5 down, it's 5 times the base 3 logarithm of x squared minus 8x equals 10. And if I divide both sides by 5, I get the base 3 logarithm of x squared minus 8x equals 2. And that's certainly more manageable. This becomes 3 to the 2 equals x squared minus 8x. Three to the 2 is 9, so when we zero the equation, that's what we're left with. And what we need to do is solve this now by factoring. I have never, and I'd bet a lot of money on this, I don't think you will ever be asked on an exam, certainly not mine, and I don't think the diploma exam, to solve a quadratic trigonometric or a quadratic logarithmic equation unless the quadratic ends up being factorable. I'd be blown out of the water if I saw something that would require the quadratic formula. Okay? Watch, it's going to happen. I think it's x minus 9, x plus 1. Which means that x is equal to either 9 or negative 1. Now, rather than talking about the domain for x, just put in 9 for x and see if the argument is positive. Okay? This is a little tricky because it's raised to a 5. The whole argument is containing the exponent of 5. But 5 is an odd number. So if the base is negative, the base raised to the 5 will be negative. If the base is positive, the base raised to the 5 will still be positive. So when we put 9 in, you are going to have to take 9 squared minus 8 times 9, and I believe you're going to get the number 9. It's going to be positive. It's going to be 81 minus 72. So 9 survives the argument test. Does negative 1? Well, when I take negative 1 squared, I get 1 minus 8 times negative 1, which will be 8. I get 9, don't I? Just demonstrate this to you. Negative 1 squared minus 8 times negative 1, I still get the same number. So these are both valid. I will tell you that algebraically there is a way to go from that quadratic being greater than 0 to telling what the domain is. And it's something you learned in Math 20, but it's something I don't think you'll ever need to worry about in Math 30. And it's so confusing and complicated in Math 20 that there's no reason to rehash it here. We solve these kinds of things in calculus using a different method, but it becomes easier in calculus. So both of those solutions are answers. Any questions with that one? Okay. I want you to take a look at G and see if you can figure out what the significant difference is between the two 2's in each of those two terms. You understand the notation here that in the first term it's log of x quantity squared, and the squared is squaring the whole logarithm, yes? But in the second term it's the logarithm of x squared. And although you do not need this set of brackets that I'm about to write, I think it's important. I want to start a movement. Yeah.
Our logarithms are base 2.
Your logarithms are base 2? Thank you. This is equal to 0. I would like to start a movement where instead of writing log base 2 of x quantity squared, I want people of the world to start doing that, just like we do with trigonometry, right? Sine squared means sine of x quantity squared. I haven't convinced anybody yet, so we're just going to have to go with what we typically write. Now, what is the difference operationally between the exponents? The answer is that this exponent is on the argument, which means we can move it out in front. The other two, in the exponent 2 in the first term, is not on the argument. We can't move it out in front. That's why that little set of brackets is important. So this becomes the base 2 logarithm of x quantity squared minus 2 times the base 2 logarithm of x equals to 0. And this is algebraically, fundamentally, no different than me saying that. It's no different. If I asked you to solve that equation for a, you would factor an a out and have left a minus 2, and then you would say, oh, that means that a is equal to 0 or a is equal to 2. Right? Because this factor would be 0 if a was 0, the other factor would be 0 if a was 2. Well, we're going to do the same thing. We're just going to factor out base 2 logarithm of x and get log base 2 of x factored out leaves me another log base 2 of x minus 2. The only way the product of two factors can be equal to 0 is if either of the factors is equal to 0. And then I add 2 to both sides. And where I'm landing here, everybody, I hope you appreciate this, is my analogy is that. Right? Except it wasn't a squared minus 2a, it was log squared minus 2 log. What does that mean for the first equation? X is equal to 1. Why? Because log base 2 of x equals 0 has an exponential equivalent of 2 raised to the 0 equals x. And here, x is equal to 4, because log base 2 of x equals 2 means that this base of 2 raised to this 2 that the logarithm is equal to has to equal x. And if you look back at the original equation, the argument was x, wasn't it? That's the only argument there was. Well, x and x squared. But both of these are positive numbers, so you'd be taking the logarithms of positives. If you wanted a domain here, your domain would be x is greater than 0. The domain for this is x can't be 0. It can be negative because when you square it, it becomes positive. But the domain for the other one is x is greater than 0, so greater than 0 means it must be greater than 0. It can't even be negative. So this one should be a breeze. We can write this down. Are these base 10 logarithms on your handout? Okay. We can write this as log squared of x. I'm just going to do it anyway. Maybe you'll do this on a diploma exam and teachers will go, hey, that's a good idea. Let's start doing that. You understand what I mean here, right? And I really believe that if a marker saw that, they're not going to get upset. They would go, wow, that's a pretty good idea, if they hadn't thought of it already. Minus 5 log of x minus 24 equals 0. Factor. Factor and solve. Log of x, log of x. Two numbers that multiply to give negative 24 and add to give negative 5 would be negative 8 and 3. This means log of x plus 3 equals 0. Be very careful here. You understand when I just said that, I don't mean log of x plus 3. I mean log of x plus 3. And even the way I wrote it, if I could go back in time, and I can because I have an eraser, I would probably space things out a bit just to make sure that everybody's clear that 3 is not part of the argument. And then here, log of x minus 8 is equal to 0. So log of x is equal to negative 3. Log of x is equal to positive 8. These are base 10 logarithms. So all we have to do to finish the question is write them both in exponential form and get x equals 10 to the negative 3, x equals 10 to the 8. And 10 to the negative 3 is 1 over 10 to the 3. It's a positive number. And again, the arguments in this equation were simply x or x to the 5, but it doesn't matter. X must be greater than 0. Are we good with that example? All right, you knew it had to happen. 4 times the base 2 logarithm of cosine of x plus 2 equals 0. This is not a difficult question. It really isn't. If we can get it to be a single log equals something, then we'll get rid of the logarithms by writing it in exponential form, and we're going to have a very basic cosine equation. The first thing I do is I subtract 2 from both sides to get 4 times the base 2 logarithm of the cosine of x equals negative 2. I can divide both sides by 4, which means the base 2 logarithm of the cosine of x is equal to negative 1/2. So the negative 2 divided by the 4 is negative 2 over 4, which is negative 1/2. And that means that cosine of x is equal to 2 to the negative 1/2. Well, what is 2 to the negative 1/2? It's 1 over 2 to the positive 1/2, which is 1 over root 2, which is root 2 over 2. And by the way, this is a positive number. So what we've kind of stumbled upon here is based on the equation. That argument is always going to be positive. We are looking now on the unit circle of where cosine of x equals root 2 over 2, which you get the point, which is at those pi over 4 reference positions. I've made a mistake. Which is at these pi over 4 reference positions here and here. And I knew I made a mistake, and this is a learning thing for you too, because I was about to explain to you, and what I would explain to you is what I would think to double check. Cosine is the x coordinate, so I'm looking at the 2 points where x is positive, which is over here in quadrant 1 and 4. So as soon as I said quadrant 1 and 2, when I started running that through my head, I went, no, that's not right, 1 and 4. These 2 positions correspond to angles, which are solutions. This didn't say find the solution to the equation in quadrant 1 or between 0 and 2 pi or anything. It just said find the solutions. So the solutions are x is equal to pi over 4 plus multiples of pi. X is equal to 7 pi over 4. Did you see me counting there? 1, 2, 3, 4, 5, 6, 7 pi over 4. plus multiples of 2 pi. Don't ask why I changed it from 2n pi to 2 pi n. It's a mystery for the ages. N is an element of the integer number set. If you want to, check out the validity of these solutions, no matter what these 2 points are, no matter how we get there, no matter what the angles are, cosine will be positive root 2 over 2. So based on that, cosine of x is always going to be positive, and that argument is a valid argument. I don't know how it would work otherwise in this particular case. I think it has to be a valid solution. Okay. Going back to the written response that I was talking about for your exam, I typically will give, as I said, something that is exponential, like from yesterday, with a common base and then without a common base. And I like to give something like this, where you end up having a quadratic, but I also ask you to identify the domain. And I want a singular domain. If I said, what is the domain of x in this situation, and you wrote these both, that is not good enough. You need to write them both and then say that x is greater than 6 supersedes everything. You get my drift? Okay, it's the true domain. So what you would do is write this out maybe and then say the domain is x is greater than 6. And if you had a number line that showed the overlap of the domains, that's pretty valuable as well.